Hey guys, we are in the midst of trying to reverse our class, and so this is kind of the first test experiment of it. Please remember what you're going to have to do is watch this at home, which you obviously are already doing, and then you need to take notes on this while watching. That is your homework each night that we're in this kind of reversal process. Make sure you bring those notes to class because I'm going to come around and check them. Make sure they're well written. Make sure that they are complete. Kind of the advantage behind this is you may pause, so feel free to pause this video at any point in time, so you can write down anything that you need to do. If you need to rewind to get back to something, then rewind, go back to whatever you need to see again, look at it again, listen to it again, try to understand it and grasp it fully. So without any further ado, let's jump straight into what we're doing right now. It's electricity and magnetism. It's this odd relationship between them. But before we talk about this relationship between electricity and magnetism, let me talk just for a moment about magnetism itself. Everybody's pretty familiar, more than likely, with the kind of the standard permanent magnet, right? I mean, on one end, there's the North Pole, right? On the other end, there's the South Pole. And you have this magnet, and it likes to stick to things that are metal, although not all metals, right? Certain ones are magnetic, certain ones aren't. We'll get to that. Other than that, this idea of a magnet, to many of you, probably was just kind of accepted for what it is, but unknown. You just weren't sure why or how it works. So magnets, in general, permanent magnets are caused by domains. So what that means is we can kind of divide this magnet up into chunks, okay? Chunks called domains, all right? Now, each domain has a direction that it's pointing, a magnetic direction, if you will. These are caused by certain materials. I need to go back and say this. Certain materials, specifically kind of in the center of the periodic table, all right? In the very center of the periodic table called the transition metals. Certain metals have unpaired electrons. So what that means in a Bohr model of the atom, right? So I have this nucleus, and this is the simplest form, right? The Bohr model. And then around the nucleus, where the protons and neutrons live in the nucleus, I have these orbitals, okay? Now, I'm going to simplify this down, to say the least here. I'm not going to go all the way out into, iron and gold and silver, where I'm putting like the gold 79 electrons around. That'd be kind of crazy. I just want to show the idea. The electrons like to live in orbitals. They live on the orbitals, and they like to live in pairs. What that means is they like to live together. So 2 can fit on the first ring, 8 on the next. 8 on the one after that. It varies by where you're looking at, right? Which type of element you're looking at from here on out. But certain ones have an unpaired guy. Now, the electrons have a spin, and we've never really talked about that. The electrons have a spin. It's part of their quantum number. It's either considered to be up or down. Now, all these electrons that have a pair, that live in pairs, one of their spins is up and the other down. So the net effect here is no spin, right? But this one unpaired guy, he has a spin with nobody to offset it. And a bunch of these guys together with spins all the same way and no one to offset them is what gives us magnetism. Now it's an odd phenomenon, and maybe as we get going to this, it will be a little bit clearer, because it's, an electron kind of leads way to electricity. There's this odd relationship between electricity and magnetism, and even the standard magnet, standard permanent magnet, just the bar magnet, is due to this relationship between electricity and magnetism. But anyway, back to our domains. These domains are caused by the unpaired electrons, right? And normally, if the thing isn't a magnet, the domains are pointing, they're just going all over the place, and Some are going up, some are going down, left, right, and I mean, they're just going every which way. This would be a magnetic material, right, that has not been magnetized yet. An example of this might be just a paper clip. If you've ever taken a paper clip and stuck it on a magnet and you pulled it away, there is some residual magnetic effect still there. You can use the paper clip to pick up other paper clips. Now, a paper clip is made of material that's not great. It quickly loses its magnetism. The domains quickly go back to scatter all over the place. But whenever you stuck that paper clip next to a magnet, what happens with it, if we can reduce that paper clip down to a bar magnet, with all these domains, right, I'm just going to kind of sketch things out really fast again here, is you get all these domains pointing the exact same way. Whenever you get all the domains lined up, you get a good permanent magnet. The more the domains are lined up, the better, the stronger the magnet, right? Now, magnetic fields. Magnetic fields go from the North Pole of the magnet to the South Pole of the magnet. The direction it points. Kind of like electric fields, remember? It was all about a direction that a positive test charge would go. This is all about the direction of going from North Pole to South Pole, like for a bar magnet. So it's going to start here at the north and kind of loop around here to the south, like this. Okay, so there's a bunch more coming out, moving back in, so on and so on as it bubbles out. Now it gets weaker and weaker and weaker the farther out you go. So this works very similar to electric fields. It's just going from north to south instead of with reference to a positive test charge. So you should already be seeing a lot of similarities here being set up. And just like you're used to, right, and what you have learned, if you bring two magnets close to each other, because they are emanating a magnetic field that is each of them, there is an attractive or repulsive force. That means that they're either going to be pulled together or they're going to be pushed away, depending on what two sides of the magnet you're bringing together. I mean, if you bring if you bring a North Pole and North Pole together, right? If we got a bar magnet like this, here's the north and south. Bring another bar magnet, and I try to bring it close to it. I use the exact same poles, just like with electricity. Opposites, right, attract and likes repel. So in this situation, there is a repulsive force where the magnets try to push away from each other due to their interaction with the magnetic fields. And the actual equation for force between two magnets here is mu, right? That's the permittivity of the space in between them. We can use permittivity of free space. It's a constant, right? It would be given to you if you actually have to solve this. Q of magnet 1, that's how strong the magnet is there. Q of magnet 2 all over 4 pi r squared. And that's kind of the historical equation. Obviously, it gets more complicated than that, but this historical equation will work for us. Now, let me just kind of point this out to you. We're not going to use this equation much, but I do want to show you this. Let me pull out these constants, mu and 4 pi, right, out here into a constant thing, and then this over here separate. What you should see here is force is equal to some constant times one magnet strength times the other magnet strength divided by the distance between them squared. My goodness, it looks unbelievably similar to Coulomb's law, right? And you'll find that lots of things seem to follow this for some odd reason. Remember universal gravitation too. I mean, let me put a Coulomb's law. F equals K out in front, charge 1, charge 2 over the radius squared. Gravitation, universal gravitation, right? Big G constant out in front, m1 times mass 2 divided by radius squared. So this kind of idea for force seems to occur all the time in our universe. It seems to be this odd link between things. Okay, and I should come back up and point this out also with magnets. Because of the domains all pointing in the same way here, the cool thing happens if you break a magnet. Right? If I take a magnet, right? Here's my north and here's my south, and I break it. What I end up getting out, two magnets, brand new, where the broken side becomes the other pole. Okay, where the broken side becomes the other pole at that point in time. You can't break a magnet in half and get a monopole. Sometimes you'll hear monopoles referred to just because it's great for doing math, it's great for conceptualizing physics, but in reality, you never ever get it. This is all standard magnetism stuff. I'm not overly concerned about it. Quite frankly, it's not all that exciting. So instead, I want to come over here to a few more exciting ideas, if you will, the interaction between electricity and magnetism. They're so closely tied that we really do call it the electromagnetic force whenever we're dealing with it. Here's kind of the idea of what we discovered. If I've got a couple of magnets, so let's give ourselves, a couple of magnets. Let's make this side the entire north pole, and so I've got a magnet extending up here. Here's another magnet in the south pole, and it's extending down there. So there's a magnetic field that goes from north to south, right? Kind of like this. What we discovered, and this was really, really odd, if I take a charge, let's make it an electron here, okay? If I take a charge and I shoot that charge through the magnetic field, right? Whenever it enters the magnetic field, it will experience a force. It's going to be pushed, okay, one way or the other. And we'll get to which direction and how much here in a little bit. Now this is really weird, especially considering that, an electron, it's not a magnet, it's interacting with magnets, and if I just took the electron and I set it in the magnetic field, it wasn't moving. If it wasn't moving, there would be no force at all. The force depends upon the moving charge. And so this leads us to this idea of moving charges give rise to magnetic fields. It's as if a moving charge behaves just like a magnet itself, okay? Which seems really, really weird and baffled physicists for a little while, and so they began to investigate. All right? What we began to find, let me come back here, not get to this just yet. What we began to find is as charges move through, right, we get a force applied to them. So if I've got a magnetic field, let's just use this picture one more time. I've got a magnetic field here. Charge goes through it. Charge goes through at some velocity. I get a force applied, and we're going to get to the left-hand rule here in a second, where it's going to be either into the board for view, the computer screen, right? Into the computer screen or out of the computer screen, which doesn't seem to make too much sense either. The initial thought is that the force would be applied and make it curve downwards. It doesn't. Anyway, coming to this. Current carrying conductor. So I want to start here, and then I want to build back to that. So moving charges give rise to magnetic fields. Moving charges give rise to magnetic fields. That means if I've got a wire, right? I've got a wire, and let me kind of make my wire a tube now. And I've got a current moving in it. That means I got a whole bunch of electrons flowing, right? I mean, these guys are flowing up in my direction. I got a whole bunch of electrons moving at their drift speed. They're flowing upwards. Well, that means, logically, if moving charges give rise to magnetic fields, that this wire is going to create a magnetic field. It does. The magnetic field is actually formed around it. And we can, this is a trick. It actually comes from a complex mathematical process. It's not too bad. But I just want to use the trick, the right-hand rule, to figure out which way the magnetic field would go. Take your thumb, point it in the direction of the current along the wire. Make sure you're using your right hand, by the way. Take your fingers and curl them around the wire. The direction your fingers curl is the direction that the magnetic field would go. So up here, right, on this example, the current is going up. That means the magnetic field is going to loop around like this. Come around, go behind the wire, come back, and go back on top of the wire. Okay? It's like this, disappearing behind and then coming back on top. Okay, all the way around. So I get this nice uniform magnetic field, at least uniform in a circular manner. As you get farther and farther out from the wire, obviously it's going to get weaker. Okay. We get this nice magnetic field coming around the wire, and I figure out the direction of the magnetic field based upon right hand. So a couple of other examples here. Let's just put a current carrying wire. Let's make the current go that way. Magnetic field, right hand rule, taking my thumb, pointing it in the direction of the current. The right hand rule is going to say that it curls around over top like this, right? Over top like this, and then disappears behind it, comes back around. Okay? Curls over the top, disappears behind it, comes back around. Okay, comes back around. I'm going to go ahead and introduce a little bit of notation here to you also, because we can deal well with the two-dimensional in drawing, but we also got to be able to deal with 3D in and out of the computer screen. I think we've talked about this before, but I'm not sure. So whenever you see this, circle with an X in it, this means that it's coming, that the current or whatever it is going into the page, or into the board. Okay? Whenever you see a circle with a dot on it, it means it's coming out of the page, okay, or out of the board. Like it's coming out of the computer screen at you, right? This gives us the idea to where we can draw 3D things. Sometimes it helps me remember these guys if I think of the into the page as the tail feathers of an arrow that was just shot, or I just shot. Okay, and so I can actually see the tail feathers flying away from me. Coming out of the page, once again, the arrow idea, this is the sharp point that's coming at your face. That's not the pleasant one, but you know, it helps me remember. All right. So if I've got a current carrying conductor or a wire, that's all that really is, going into the board, right? So the wire is starting out where you are and is traveling from you into the computer screen and going through the computer screen, right? Which way is the magnetic field going to go? Which way is the magnetic field going to wrap around? By the way, it's all about clockwise and counterclockwise. It's all circles, right? So I take my thumb, I stick it on my right hand, and stick it going into board, right? Then I'm going to take my fingers and wrap around. I see that it goes clockwise. Okay? So that's right here. Now, let's talk about force being applied to a moving charge, a magnetic field. Right? Forces are applied to moving charges in magnetic fields, which we've already said. Right? So we have this idea set up where I got this magnet, I got these magnets here, right? And, so there's a magnetic field, and I said an electron, any charge will do, as long as there's a charge, you shoot it in, you get a force. So this force behaves according to this equation. F equals. Now, note, I'm talking about a charge, not current here right now. We'll get to current here in a second. QV, let me not make that a beta, that's a B. QVB sine theta. QVB sine theta. Where Q is the charge, right? Is it 1 coulomb? By the way, that'd be huge. You know, if it's 2 electrons, it'd be 2 times 1.6 times 10 to the negative 19 coulombs, right? But how many coulombs is it? And maybe we should put that down. Unit coulombs, right? Capital C. V is the velocity measured in meters per second, which implies and actually is the fact if a charge is moving faster, there's actually more force applied to it. B is the magnetic field strength. Magnetic field strength, and that's measured in Tesla, capital T, Tesla. Okay, in sine theta, it's kind of self-explanatory, except when we talk about the angle here, sine theta. In other words, there's a little bit of space here. Pull all this stuff down. In other words, if I've got a magnetic field going like this, okay, magnetic field B, the maximum force that I can have, is if the particle, right, my electron, is shot at a 90-degree angle to the field, because sine of 90 degrees is 1, right? Sine of 90 degrees is 1, and then 1 times my QVB gives me the highest number I can have. Anything less or greater than 90 degrees, 60 degrees, 40 degrees, so on and so on, is going to give me some decimal number, and it's going to reduce the overall force. Okay, so this idea right here, if I have a magnetic field going, let's once again make it go to my right, and I shoot a charge, let's make it an electron again, at an angle through it. By the way, the angle that you want to use is the angle measured to the magnetic field. Let's say 45 degrees here. Okay? Sine of 45, square root of 2 over 2. That's a decimal number, right? And so you're actually coming out with something less than 1, thus reducing force. Likewise, let me spin the page to pull stuff down here. What if we shot it at the exact same direction as the magnetic field? What if we shot our electron in the exact same direction as the magnetic field? Well, if I did that, sine of, what is this angle between it? Well, it's 0 degrees, right? Sine of 0 is 0, right? Meaning that QVB sine theta, that's charge Q times velocity V times B, magnetic field strength. Sine of 0 is 0. 0 times anything is 0, giving me whenever the charge is going the same direction as the magnetic field, there is 0 force, no matter what. It's all about having a maximum force, this right angle. It's right angle, right? Now, this idea right here is how we're going to calculate the magnitude, right? The number of it. But force here isn't a scalar. It isn't just a magnitude. It's a vector, meaning that it needs a direction, right? So I gotta apply a direction to this thing. The way I'm gonna do that is by using left-hand rule. Okay, by using left-hand rule. Right. Now, I know we just had a right-hand rule, right, for figuring out which way a magnetic field wraps around, for figuring out which way a magnetic field wraps around a current carrying wire. This is left-hand rule here, right? This is all about determining the direction that the force is being applied to a charge moving in a magnetic field. Take your index finger here. Take your index finger and point it in the direction of the magnetic field. Take either your middle finger, or I just use all the others, and point it in the direction of the charge. And we're going to get the current later. Okay? Point it in the direction of the charge, Q. Stick your thumb up. Now, all of these things should form a 90-degree angle. Okay? Stick your thumb up. That's the direction the force is going. So, for example, in my problem on top here, using my left hand, and I'll get to this idea right now. Let's not make this an electron. Let's make this a proton. Otherwise, this isn't going to work. I take my index finger and I'm going to put it down. I take all my other fingers and I'm going to rotate them, right, to where they're pointing to the right. I stick my thumb out and I see the force here. The force is going into the board. The force is going into the board at that time. All right? Now, I should say this with electron rule. Just like with electric fields, right? This is done for a positive charges. Positive charges. Negative charges are backwards. Negative charges are backwards, meaning that top, this for a proton, right? This, if we were dealing with an electron, force would be coming out of the board or out of the computer screen etching, right? It'd be coming out etching. So a couple of examples of this where we're just going to quickly draw things out. If I have a magnetic field going up, I have a magnetic field going up, and I have a particle, let's make it a positive particle, being shot through. Left-hand rule is taking my index finger, sticking it up, taking my other fingers, right in the middle and all the others, pointing to the right. My thumb pokes out. That means the force here, the force is out of the border, out of the page. Right? Another. Let's give ourselves a magnetic field going into the board. Give ourselves a magnetic field going into the board. And now I'm going to take the same positive particle and I'm going to shoot it the same direction. Over to the right. Use left-hand rule to figure out which direction the force is going. Right, so index finger goes the direction of the magnetic field into the board. So you point your index finger at the computer screen. You take all your other fingers and you point them in the direction of the positive particle. And I recommend whenever you do this, start with the index finger and then take your other fingers and rotate them. Okay, it's like you're rotating your wrist, right? So I'm going to rotate my wrist so that the other fingers are pointing the same direction as the positive particle, going towards the right. Stick your thumb out. And my thumb says the force goes straight up. So the force is going up the page, or up the board. Good. Up the board. We'll do a few more example problems like that in class. Now, let me work a couple of problems. All right. Let me work a couple of problems. Number one, how much force would an electron experience if it was shot perpendicular through a 5.5 MT, that's standing for millitesla, magnetic field at 6% the speed of light? Right. So just to get the math of this, and then let me draw a picture of what we have going on here. So once again, I have a couple of magnets, right? I have a couple of magnets, something like this. Okay, something like this. And so the magnetic field is going from north to south. And I've got a particle, specifically an electron. I've got an electron that's being shot through it. Right? Whenever it enters the field, it's going to experience a force and thus current. Now, the field has a magnetic field strength B. 5.5 times 10 to the negative third Tesla. That's what milli means. Right? And the electron here, the charge, Q, equals 1.6 times 10 to the negative 19 coulombs. Right? So to get the force, it's just kind of plug and chug here. F equals Q, B sine theta, where theta here is 90 degrees, right? So that sine of 90 degrees is 1, so this just becomes F equals Q dB, and so my force is going to be my charge, 1.6 times 10 to the negative 19 times my magnetic field strength. Let's do the velocity next, like I have it written. 5.5. Let's see, here we are, 6% the speed of light, that's 0.06 times 3 times 10 to the 8 meters per second. And that times the magnetic field strength, 5.5 times 10 to the negative 3. Right, so you pull out your calculator and you plug and chug away. All right, and we come out with what would seem to be a very small force. About 1 point, and I got, 2 sig figs here, so 1.6 times 10 to the negative 14 newtons. Newtons being the unit of force. And that seems like a teeny tiny force. Remember, we're dealing with a teeny tiny object, just an electron. Now let me pause for a second and talk about the velocity here. That is 6% the speed of light. 6% here, right? 6%, 0.06, right, in decimal form. And the speed of light, c, 3 times 10 to the 8 meters per second. Right, so that's the velocity part of it, and wanted to point that out to you. Let me point out that this force actually isn't as small as you think it is. That on the electron, this thing's actually really big. Let's look at the acceleration the electron would experience. And this is just as simple as Newton's second law, F equals ma, right? So now I've got a force of 1.6 times 10 to the negative 14 equals a mass. Now the mass of the electron is very, very small. It's 9.11 times 10 to the negative 31st kilograms, right? Times my A. So now I just divide both sides by 9.11 10 to the negative 31st. So I got 1.6 10 to the negative 14 over 9.11 times 10 to the negative 31st. Plug and chug, and we get ourselves an acceleration. All right, we come out with about 1.8 times 10 to the 16th meters per second squared. So what seems like a very small force, in all reality, is very massive, because it's being exerted on such a small mass, the electron. All right, guys, so that's an intro. That's kind of the beginning of all this. And surprisingly, this unit is relatively short, so we don't have too much farther to go. Just a couple, maybe 2 or 3 more lectures on this, and we'll be done with this unit ready to test, so it's not that large. Make sure you have the notes on this to show in class tomorrow. And I will have problems for you to work in class. Remember, this is the reversal. What you did for homework, you'll do in class. That way, I'm around to be able to help you with any questions. Make sure you also write down any questions you have from this, because I'm going to open up the first part of class, just in general questions about anything that you saw in this lecture. Anyway, see you tomorrow.